Hello students, welcome back. Today's topic is antiderivatives. Effectively, we are going backward from this point on. Up to now, for several weeks, we had been discussing the derivatives, the computation, and the applications. We now take an opposite point of view. We study antiderivatives and antidifferentiation. An antiderivative is a function whose derivative is given as f of x. Kind of like this. Capital F prime of x is equal to f of x. This capital F is called an antiderivative of f of x. We use rather complicated notation like this, which we call indefinite integral notation. Capital F of x is integral f of x dx. It has three important components. Integral f of x dx. So if you use one of them wrong, missing or misusing, of course you'll have to expect some deduction. Now, I don't see a lot of mistakes in the original function part, which we call the integrand. Just a name, but I'm going to use it often, so please get used to it, the integrand. Not many mistakes there, but I cannot say the same about the other two. This symbol is called the integral symbol, and that marks the starting point of this antiderivative computation, or which we call integral computation. They're the same. And then followed by the original function f of x. Finally, you opened up, you have to close it. Close it by dx. So kind of like this. Integral is kind of like opening up a bracket. Dx is closing the bracket. Missing or misusing integral symbol, that's usually a little bit more severe. I give -2 deduction. Missing dx, a little bit more prevalent, but almost equally as severe. I give -1 deduction for each mistake. Now, the maximum deduction I've ever gave for missing dx's in a single exam was -13. -13 in a single exam, that's enough to knock off a B student all the way to D. Basically, that's what happened, as a matter of fact, completely bypassing C. That was mind-boggling. And okay, I don't do that anymore. That was when I was student instructor and I was following the captain professor's very, very strict rating scale. I don't do that anymore, but still, I do scrutinize missing dx's, and missing dx -1 up to a certain cap I will not disclose. It depends heavily upon how well the students do. Kind of like curving. But missing dx is 5 such mistakes and then you're losing about 5 points in the exam. Those kind of things are commonplace. So please be warned. Now, in this video, we're going to focus almost entirely upon the notation and some theory part, not the computation. So let me tell you a little bit more detail about this dx. Why is it so important? Number one, I already said it. It's a closure. We opened up this computation with integral sign. We have to close it. That's number one. Number two, it marks the variable. The function is with respect to variable x in this time, f of x. So we use x. If you have f of y, then you use dy, and then you can be du, dv, dt, it can be anything. Even more so if you have more than one character, like a or b as parameter, and then we have x or y. Well, in that case, it's really important to tell everybody which is a variable and which are just coefficient or character. That's reason number two, specifying the variable. Number three, change a variable. Sometimes you change a variable. And how do you do that? It is related to integration by substitution, which is the chain rule in antiderivative version. It's very, very important, but something we're going to discuss in a couple of weeks, not right now yet. That's reason number three. And there's another reason, number four, which we'll discuss in Calc 2. It's related to Riemann sum. Anyway, there are at least 4 important reasons why dx is so important. So if you miss it, well, please expect deductions here. Please be warned. Now another aspect, integral constant. This is related to why this notation is called the indefinite integral. Also, another thing here. And we say capital F of x is an antiderivative of f of x, I said over here. Not the antiderivative. We say the derivative, yeah, but not the antiderivative. On the antiderivative. Why? That's because antiderivatives are not unique. There are infinitely many of them. Here's an example. An antiderivative of 2x is x squared. Yeah, that's right, if you take the derivative of x squared, and we have 2x. But what about what about x squared plus 1, or x squared minus 17, x squared plus square root of 5, x squared plus any plus c as a matter of fact? They're all okay because the derivative of this plus c is going to be 0 anyway, so we end up with the same derivative function, which means for arbitrary c value, we have an antiderivative. So there are infinitely many antiderivatives. This arbitrary constant c is often called the integral constant, and this is going to be important in applications in physics and engineering. UNT Dallas is not really heavily engineering oriented university, so I'm not going to take up any points for missing c in this course. Of course, if I teach this course in some other institution, and that institution is heavily in science and engineering, and of course, in that case, I'm going to start taking some point off for missing c's, kind of like missing dx's, but not here. But I still give you some warning. Okay, so much for notation issues, and let's discuss a little bit about antiderivative rules and just a little bit of theory. Computation part will be discussed in the next segment of the video. Here's a trivial rule. Antiderivative of 0 is constant c. Antiderivative of k is kx plus c. How do we know? No sweat. Start from the right hand side and take the derivative. You see? Antiderivative, that's backward computation of the derivative. So just take the derivative from the right hand side. Derivative of arbitrary constant c, that's 0. Derivative of linear function kx plus c, that's k. And that's how you prove this. How about the next rule? Antiderivative of sum is sum of the antiderivatives. Why is that so? Again, that's because the derivatives act exactly the same way. This, by the way, is the entire proof. Next, how about coefficient? You can multiply coefficient before or after. That's because the derivatives behave exactly the same way. A bit of warning, by the way, related to this one. Antiderivative of sum is equal to sum of the antiderivatives. Yes, but not the product or quotient. Antiderivative of product is not the same as product of the antiderivatives. Same for quotient. We have such a thing called product rule and quotient rule, I think. Do you remember? Derivative of u times v, what was it? It wasn't u prime times v prime. No, that was not true. What do you have instead? U prime v, oops, u prime v, let's write completely here, is equal to u prime v plus u v prime. That was it, isn't it? It wasn't just u prime times v prime. So this is basically an incorrect version, this is a antiderivative version of an incorrect use of product rule. Same goes to quotient rule. It looks simple now, but over the years, I've seen a lot of students making these mistakes here. So I emphasize again. We're going to emphasize these again when we do computation in next several segments of the videos, but let's start it now. Antiderivative of sum is sum of the antiderivative. That's okay. But The product or quotient? No. Okay, some more antiderivative rules here. Power rule, the power function. Now, how do we take the derivative of a power function? It goes like this. Derivative of x to the m power. How does it work? We multiply the power and subtract 1 from the power, isn't it? That is the power rule for derivative. What if we go backward? That's basically what this is. Add 1 and then divide. Here, if we replace m by this k plus 1, this is what we're going to get. Instead of m, let's replace it by k plus 1 power. So multiply by k plus 1 and subtracting 1 from the power, we get just k power, right? And then we just divide k plus 1 from both sides. This is what we get. 1 over k plus 1 is equal to that. And that's precisely what we are looking for. If you take the derivative of this, as a matter of fact, this is coefficient, so I can just slip it. Oh, sorry about that. I can slip it inside the derivative. Okay, all right. So derivative of this is extra k power. So this is an antiderivative. It goes right here, and then, as we discussed before, arbitrary constant plus c follows. That's how it works. Or of course, if you want to take shortcut, you can simply take the derivative from the right hand side. It's an easy computation. There's an exception though. When k is -1, k plus 1 is going to be 0, and you cannot divide by 0. So that's an exception. That exceptional case is the next. Antiderivative of x to the -1st power, or equivalently speaking, antiderivative of 1 over x is log of x. Why do we need absolute value here? Because inside of the logarithm always have to be positive. To be a little bit more precise, we need these computations. Derivative of log is 1 over x, so you have x to the -1st power. That's okay. But what if x is negative? In that case, you have to make it positive by taking extra negative sign here. So this gray part, which is a little bit harder, so I'm not going to emphasize to everybody, but for interest students, here we go. When x is negative, derivative of log of -x, we use chain rule to calculate, and then we're going to get 1 over x anyway. But I don't want to emphasize the middle part very much. When I did that, I see a lot of students making this kind of mistakes. Kind of like this. I mean, they're so captured by reciprocal, they use it all the time for some other things. For example, like this. And then write it as log of, kind of like that. That's incorrect. I'm sorry, I see this kind of answer a lot. This is not 1 over x, this is 1 over e to the x. But because of this reciprocal things, students make this mistake a lot. But if you consider upon -1st power, then no such mistake. And finally, this one, that's easy. Antiderivative of e to the x, well, the derivative of e to the x stays the same, so antiderivative stays the same too. These are basic antiderivative rules. So what did he do in this first segment of the video? We discussed some basic antiderivative rules, some trivial rules, and most of all, we talked about antiderivative notation, and even more importantly, the grading scale. Missing dx, that's important. Please be warned.